Welcome to Lecture 19, the first of two lectures that deal with the behavior of fluids. And before I say another word, I'd like you to look at a piece of fluid behavior. Over here, I have a beaker of water. It's full to the brim. It's got some ice floating in it. And I really want to point out how full it is. It's full right up to that little spout that water can pour out of. There's not room for another ice cube. There's not room for any more water. There's not room for any more volume to be added to that beaker, or water would pour out and it would wet the paper towel down below, which right now is perfectly dry. So we're going to leave that. We're going to come back to it at the end of the lecture. There's the first of our demonstrations. Okay, let's talk about fluids. What is a fluid? Well, fluids are materials like liquids and gases that are free to distort and change their shape. We're going to be spending two lectures on the behavior of fluids. This lecture is about fluid statics, fluids that are at rest. In the next lecture, we'll talk about fluids that are free to move. So in these two different kinds of fluids, liquids and gases, in a liquid, the molecules are very, very close together, but they're free to move past each other, unlike a solid where the molecules are locked in place in a regular crystalline structure. In a liquid, they're free to move around each other, but they're closely spaced, and that makes a liquid essentially incompressible. It's very difficult to change the density of a liquid, and we make the approximation liquids have constant density. In a gas, on the other hand, the molecules are very distant. They're moving all around quite randomly, and it's quite easy to change the volume of a gas. In both cases, the behavior of a fluid could actually be calculated by applying Newton's laws to all the individual molecules making up a fluid. But that would be a computationally impossible task. And so what we do is approximate fluids as made up of continuous matter. That is, we're kind of averaging over distances that are large compared to the size of an individual molecule. And we're treating these fluids as something they aren't, namely absolutely continuous matter. And then we can characterize them by just a few simple properties. And let's look at some of those properties of fluids. The properties we're concerned with are density and pressure in this lecture. In the next lecture, we'll add fluid velocity as well. But here, we're dealing with static fluids, fluids that aren't moving, and we're just going to talk about these two characterizations of a fluid. What's density? Density is the mass per unit volume of the fluid. How much matter is crammed into a given space? What's the mass per unit volume? Its symbol is the lowercase Greek rho. That's not a p, that's a lowercase Greek rho. Its SI unit, because its mass per unit volume, is kilograms per cubic meter. And pressure is the second of the two quantities we want to work with. Pressure is the force per unit area that a fluid exerts on its surroundings, on its container, that a piece of fluid here exerts on the adjacent fluid. Pressure is force per unit area. Its symbol is a capital P, and in the SI system, its units are the units of force, newtons, per the units of area, square meters, newtons per meter squared. And 1 Newton per meter squared is called a Pascal, after the mathematician Blaise Pascal, for whom the computing language Pascal is named, among other things, and the unit of pressure is named after Pascal, capital PA, capital P because it's a unit named after a person, but when we write the unit out, we write it in lowercase. Other pressure units you will have heard are PSI, pounds per square inch, in the English system. Sometimes you'll hear, by the way, PSIG, which means how much pressure there is above atmospheric pressure, called gauge pressure. Inches of mercury, I'll show you shortly where that one comes from, but it has to do with mercury barometers. Millimeters of mercury, same thing, but with a metric unit. And we'll often talk about pressure in atmospheres, where 1 atmosphere is defined as a standard value for the Earth's atmospheric pressure, which, of course, as you know, varies with meteorological conditions. An important thing about pressure is that it's exerted equally in all directions. It exists throughout a fluid. It isn't like there's a pressure force this way in one direction, one place, and a pressure force this way in another place. Pressure exists and is exerted in all directions throughout a fluid. By the way, there are interesting exceptions to that. When you have a fluid that is magnetized, for example, and is electrically conducting, you get a preferred direction. You can actually get pressures that are different in different directions. But in the everyday fluids we deal with, like water and air, pressure is exerted in all directions. So here's a picture that suggests a region of fluid right at the center of a container full of, say, liquid water. And that pressure is being exerted in all directions. Upward, sideways, downward. Doesn't matter. Pressure is exerted equally in all directions. And at the interface where the fluid meets its container, give a little area A of that container wall, and there will be a force given by the pressure times that area, because pressure is force per unit area. So those are the two quantities we're going to be using throughout this lecture to characterize fluids, density and pressure. This lecture is about fluid statics, fluids that aren't moving, and so we want to talk about the conditions that put fluids in static equilibrium. We've already talked about static equilibrium in mechanical systems, and we know the key concept there is that there be no net force. So we want to understand and explore the conditions that there be no net force on a fluid, and therefore the fluid will be in static equilibrium. And I'm going to talk about fluids that are here on Earth or somewhere else in the presence of gravity, because that's the other force we're going to have to balance. So let's talk about hydrostatic equilibrium. What is hydrostatic equilibrium? Hydrostatic equilibrium is the condition in which there is no net force on a fluid, and as I say, the fluid I'm going to talk about is in the presence of gravity. So here I have a picture, and the picture shows a container full of fluid, and we single out a small cylindrical region, an element of fluid, that small flat disc-like cylinder in the picture, and that element of fluid will be in equilibrium with the surrounding fluid if the net force on it is zero. And we want to explore conditions in which that net force will be zero. That requires an upward force to balance the downward force of gravity, and that upward force has to be due to pressure. Now, here's the thing about pressure. Pressure itself exerts a force per unit area, but the only time we experience a net force due to pressure is when there are pressure differences. For example, right now there's 14.7 pounds per square inch pushing on me associated with atmospheric pressure. In particular, it's pushing in on my eardrums. But I'm in equilibrium and the pressure inside my body is also 14.7 pounds, so that's pushing out and there's no net force on my eardrums. If there were, I would feel pain. And that's what you feel when you go up in an elevator very rapidly or drive rapidly up a mountain road or an airplane's cabin changes pressure. You feel that pressure difference. It takes pressure differences to give rise to forces. And so in static equilibrium here, we need an upward pressure force, and that means we need bigger pressure at the bottom than at the top. So that's the condition for hydrostatic equilibrium. Let's explore that a little more quantitatively. So let's do the math. So here's our picture. We have a fluid, and we have an element of that fluid singled out, and we want to ask the conditions that that fluid element be in static equilibrium. We have an area A for that fluid element. The element has a thickness delta H. We're going to designate H going downward as the depth of this fluid. There is a gravitational force downward on the fluid. And now, sorry, there's a force on there's a gravitational force downward on the fluid. There is a pressure force upward on the bottom of the fluid, and I'm going to designate that as P plus delta P times the area. The delta P indicates that the pressure is greater at the bottom than it is at the top. At the top there is a pressure PA. On the bottom there's a pressure P plus delta PA because the pressure is bigger at the bottom. So I want to find the net force on this thin cylindrical fluid element with area A and thickness delta H. The downward force from pressure on its top is PA. The upward force from pressure on its bottom is P plus delta P times A. And the net pressure force is therefore their difference. P plus delta PA pointing upward minus PA pointing downward. Do the math. Multiply out the first term. P times A is PA. Delta P times A is A delta P. Then minus PA cancels the first PA. And all that matters, as I said before, here it is mathematically, is the difference in pressure. There is a net pressure force on that disc-like piece of fluid only if there is a pressure difference across it. The pressure can be as big as you want. It can be 1,000 atmospheres down and 1,000 atmospheres up. And there will be no net pressure force unless there's a difference between the pressure at the top and the pressure at the bottom. So here's the upward pressure force we found. The pressure force is the area times the pressure difference across that distance delta H, in this case, the thickness of our fluid element. There is also the downward gravitational force, mg. There it is. That's the gravitational force, the weight of the object. Gravity doesn't care that it's submerged in a liquid. It still exerts the force mg. And the mass of this particular piece of fluid is the density of the fluid times the volume, because density is mass per unit volume. So you can get the mass back from the density if you know the volume, multiply the density by the volume. By the way, the multiplication works only if the density is uniform. If it's not uniform, we got to use a little calculus. But here it is in this case. We assume uniform density because it's a liquid. That's the density rho times the volume of that fluid element, and the volume is its area times its thickness. So there's the mass. So the downward gravitational force, Fg, becomes the mass, mg, times the mass times the gravitational acceleration, g, and there's the mass, rho a delta h, rho times volume, density times volume. So there's the gravitational force. And we're almost done. Question we really want to ask is, how does the pressure vary with this depth h in order that this thing be in equilibrium? We know we need more pressure at the bottom. How much more? Well, the upward pressure force we found is F pressure is A delta P. The downward gravitational force, here it is rho A delta Hg. In equilibrium, those two are equal, or one is up, one is down, but they vectorially sum to 0. They're equal in magnitude. So I've equated them here, and we can do a little bit of algebra on that. I'm going to divide the delta P by the delta H, and I'm going to put the A on the everything else on the other side. The A is going to cancel. There's no A left. There's an A on both sides. That cancels. And I end up with delta P over delta H is rho, the density, times the strength of gravity. In liquids, where rho is constant, the pressure increases uniformly with depth. So the pressure, that's what that's telling us. It's telling us the rate of change of pressure with depth is a constant if the density rho is a constant. So in a liquid, which has to have constant density because it's very difficult to change its density, to compress it any further, the pressure increases then uniformly with depths. It starts out with whatever pressure there is at the surface of the liquid, and it goes with increasing pressure as we go downward. That's hydrostatic equilibrium. That's the condition of hydrostatic equilibrium, in this case, final equation with constant density. Let's do an example. Here's the problem. Let's find the pressure at the bottom of a 30-foot deep, that is 10-meter lake, and then at the bottom of the Gulf of Mexico, where the 2010 Deep Horizon oil disaster occurred. That's 1,500 meters down, about a mile. And at the bottom of the deepest point in the ocean, the 11-kilometer deep Marianas Trench. So let's do that. These turn out to be all the same problem. Facts. Water has a density of 1,000 kilograms per cubic meter. The gravitational acceleration is close enough, 10 meters per second squared, 9.8, but let's call it 10. The atmospheric pressure at Earth's surface, approximately 100,000 pascals, 100,000 newtons per square meter. And we know in hydrostatic equilibrium, the pressure at depth is the pressure at the surface plus this rho GH. So for the lake, rho GH is 1,000 kilograms per cubic meter. G, 10 meters per second squared. The depth, we're talking about 10 meters. That's 100 kilopascal, which is an atmosphere, basically. So that immediately tells us that water pressure, on Earth anyway, increases by 100 kilopascals, that is 1 atmosphere, for every 10 meters of depth. That's a nice, convenient rule of thumb. So we immediately have the answer to our problem for the lake. The water pressure increases by 100 kilopascals for every 10 meters of depth. That is 1 atmosphere. So the lake, we're at 200 kilopascals. That's what we had at the surface, plus this additional 1 atmosphere that we got for going down 10 meters. So we're at 2 atmospheres, double atmospheric pressure by going down only 30 feet. At the deep horizon, we're down 1,500 meters. Well, we increased by 1 atmosphere for every 10 meters, so we've increased by 150 atmospheres. We had the additional atmospheric pressure at the top, and therefore we're at 151 atmospheres. That's a ton of pressure per square inch. And in the Marianas Trench, it's a crazy 1,100 atmospheres, a huge, huge amount of pressure. So that is an example of hydrostatic equilibrium, where we've done the numbers. Let's take a little stronger look at pressure, a little more detailed look at pressure. What does pressure come from? It ultimately comes in a situation where there's gravity from the weight of the overlying fluid. So here is a hunk of fluid. It's got a height h, it's got a mass m, it's got a weight mg, it's got an area a. The pressure is simply mg over a. But don't think of that as just a downward force, because if this is a fluid which is free to deform, that pressure is exerted in all directions. For a liquid, the mass is the density times the volume, density times the volume, the height times the area, and so P is rho GH. That's the pressure at the bottom, and plus any extra pressure that was at the top. So we have, by this example, gotten back to our earlier result. For gases, density varies, and I'm not going to go into the details, but it turns out if the temperature is constant, a little bit of calculus yields the fact that the pressure drops off exponentially from the surface as this e to the minus, e is the exponential base, the base of natural logarithm, so you exponentiate e to the minus the height divided by something called h naught. It's called the scale height. And for Earth's atmospheric pressure, that's the approximate expression for the pressure. The pressure at the surface is about 100 kilopascals, 101.3, 14.7 psi, 760 millimeters of mercury. Why inches or millimeters of mercury? Because that's how a mercury thermometer works, a mercury barometer works. A mercury barometer works by the pressure of atmosphere pushing down on mercury and pushing the mercury up in a tube where there's a vacuum at the top, and standard atmosphere supports 760 millimeters of mercury. This H naught is about 5 miles, 8.2 kilometers for Earth. There is no top of the atmosphere. It just fades off. And at H naught, the pressure is about a third what it is at the surface, about 5 miles up, kind of altitude where airplanes fly. And half of the atmosphere's mass, it turns out, lies below about 6 kilometers, about 4 miles. So when you're up in an airplane, you're typically above half of Earth's atmosphere. I should point out one other aspect of static pressure, and that is that pressure is transmitted equally. If you increase the pressure a little bit in a fluid, that increase is transmitted throughout the fluid, and that has many practical manifestations. You see two of them here, a hydraulic lift where you can push with a relatively small force to increase the pressure on a narrow diameter cylinder, and that will cause the same pressure increase at the other end, and that will cause a much bigger force on a much bigger cylinder. You aren't getting something for nothing, by the way. You can think about the work involved in doing that. And on the right, you see a hydraulic shovel with several hydraulic cylinders, which use that same principle to actuate the mechanisms of that shovel. Well, let's move on now and look at another aspect of fluid statics, and that is the question of why some things float and some things don't. So here's a picture of just a fluid, a container full of water, and an odd-shaped piece of the fluid, and I'm assuming this fluid is in hydrostatic equilibrium, and that means the upward force of pressure balances the downward force of gravity. So the upward pressure force, which I'm calling FB because it's going to stand for buoyancy force, balances the downward pressure force. So the sum of all these pressure forces coming in from all sides of that odd-shaped piece of water, it's just a piece of water, they balance the gravitational force, and the thing is in equilibrium. If I replace that funny-shaped piece of water with a solid material, that wouldn't change in any way these forces that are coming in from the surrounding water. But it would change the gravitational force, because if this thing weighs differently than the water, then it's going to experience a different gravitational force. So we've replaced the water with a solid object. The pressure force doesn't change, but the weight may. In equilibrium, these two forces are equal, the gravitational force and this buoyancy force on the water. If the gravitational force is less than the buoyancy force, the object's going to experience an upward force and it's going to float. That will be true if the density of the object is less than the density of the fluid. If the gravitational force is greater, the object sinks. That's true if the density of the object is greater than the density of the fluid. So that's the origin of the buoyancy force. And Archimedes' principle, discovered in ancient times by the Greek Archimedes, says that the buoyancy force on a submerged object equals the weight of the displaced fluid. And you can see why that is. If I put an object underwater, it pushes water out of the way. It displaces an amount of water equal to its volume. But the weight of that water is equal to the weight of a volume containing that same substance, that same mass, and so the buoyancy force becomes simply the weight of the displaced fluid, in this case the displaced water. Let's go over and look at some examples of that. So here I've got a lump of clay. Its density is greater than that of water, so when I drop it into the water, down it goes. Here I've got a rubber ball. If I push it underwater, I can feel an upward force. And that upward force is the buoyancy force and ultimately pushes it up. Here's the styrofoam ball I compressed when I was experimenting with Newton's third law. It's very much less dense than water, so it floats very high. Block of wood is closer to the density of water, so it floats somewhat lower. So there is the principle of buoyancy. Buoyancy is a force that's caused by ultimately the pressure difference across a fluid, and the buoyancy force is always there. Even an object that's sunk has a buoyancy force on it. In fact, objects that are underwater weigh less, or apparently weigh less. If you try to carry a heavy weight underwater, it seems to weigh less because there is that buoyancy force. But if the object is less dense than water, then the buoyancy force will actually bring it up to the surface. Let's look at some more examples of buoyancy. Here's a special case of what's called neutral buoyancy, and that occurs when the object's density equals the fluid's density. So this hot air balloon is floating at a constant altitude, and by turning on the hot air jets, the operator, the pilot, can adjust the density of that balloon and make it float level. The fish has something called a swim bladder, an gas-filled organ in it, and the fish can adjust the amount of gas in that organ to adjust its average density, and so it too can float neutrally in the water, neither rising to the surface nor sinking to the bottom. And the same thing happens with a submarine, which takes seawater into tanks that then allow it to adjust its buoyancy so it can either go down or go up, or when it's cruising along below the water, be in neutral buoyancy. The story has it that Archimedes used his principle to help the king determine whether the king's crown was a fraud or not. And here's how Archimedes did that. Archimedes recognized with his principle that the buoyancy force equals the weight of the displaced fluid. And again, the reason that is because when I have that piece of fluid that is in equilibrium, the buoyancy force on that fluid to hold it in hydrostatic equilibrium is its weight. So when I replace that fluid with something else that has the same volume, I still have the same force on it, and that force is the force that held the liquid in static equilibrium, so it's the weight of the displaced fluid. So here I show the king's crown balanced with an equal weight of pure gold across a balance, and the fact that they balance indicates that they have exactly equal weights or equal masses. Now you submerge that system in water, and what purportedly happened in the case of the king's crown is the two went out of balance. What does that mean? It means the buoyancy force on the crown is greater than the buoyancy force on the pure gold. And what does that mean? Well, it means that the volume of the king's crown has to be greater than the volume of the pure gold. Why? Because the buoyancy force on the crown is equal to the weight of the displaced water. The buoyancy force on the pure gold is the weight of its displaced water. There's a greater buoyancy force on the crown. The crown, therefore, displaced a greater mass and, therefore, a greater volume of water. And so it must have lower density. And since gold is a very dense substance, the conclusion was that the king's crown was a fraud. We do the same thing today by what we call hydrostatic body fat testing. It's pretty hard to measure the density of the human body, but measuring that will tell you something about the fat content of the body. And so what we actually do for precise measurements of the body fat content is to submerge the body in water in some kind of scale-like arrangement, connect it to a scale, and weighing underwater, sort of a modern version of the Archimedes crown experiment, tells you something about how much fat there is in the body, because it tells you something about the density of the body, because fat has much less density than muscle tissue. Okay, well, let's do an example here about buoyancy and floating objects in particular. Let's look at the question of the tip of the iceberg. You know, you always hear this phrase, tip of the iceberg. I want to ask the question, what fraction of the iceberg's volume is submerged? Well, it looks like it's a lot, and we know it's a lot. Can we prove that? Fact, for Arctic icebergs, varies with where they're from because it has to do with how much rock has gotten trained and other things like that. The density of an Arctic iceberg is about 86% that of water. 86% of that of water. It's less than that of water, 0.86 times that of water. Archimedes says the buoyancy force is equal to the weight of the water displaced not by the entire iceberg once it's floating, but by the submerged portion of the iceberg, because that's the only part that has displaced any water. So the buoyancy force is the weight of the displaced water, not the weight of the whole iceberg. So F buoyancy is the mass of the water displaced times G. If we're floating in equilibrium, that buoyancy force floating at the surface, that buoyancy force is supporting the entire iceberg. So the buoyancy force also has to be equal to the weight of the entire iceberg. F buoyancy is m ice times G. So what that means is m water times G is m ice times G. The G cancels, and we conclude that the mass of the water that was displaced by the iceberg is equal to the mass of the entire iceberg. And that's generally true. When you float an object in a liquid, the mass of the liquid that's gotten displaced is equal to the entire mass of the floating object. Why does that have to be? Because in equilibrium, that entire mass is supported by the buoyancy force, and the buoyancy force is the weight of the displaced water. So let's do the numbers for our problem. We've got that the mass of the displaced water is the mass of the ice. Well, we don't know masses so much here, but we know density. Density is mass per volume, so mass is, again, density times volume. So writing these two masses in terms of density and volume says the mass of the displaced water, that is density of water times the submerged part of the iceberg's volume, is equal to the density of the ice times the volume of the entire iceberg. Left-hand side is the mass of the displaced water, depends only on the submerged portion of the iceberg. Right-hand side is the mass of the entire iceberg. Take that, do a little algebra on that. The ratio of the submerged portion to the entire iceberg is the ratio of the density of ice to the density of water, and that's 0.86. So the tip of the iceberg is only 14% of the iceberg's mass. 86% of it, exactly the proportion that the iceberg's density was less than that of water. That's the part that's below the surface. So there's the tip of the iceberg. Let's just leave that on, and let's look at our floating items in the aquarium again. Here is my styrofoam ball, which is very, very much less dense than water, so it floats with quite a bit of its mass above the water. Very little is submerged. The opposite of the iceberg. Here is my block of wood. It's gotten a little bit saturated. It's floating quite low in the water because its density, like the iceberg's, is only a little bit less than that of water. And this red ball is floating with about half of itself submerged, which immediately tells me its density is about half that of water. Well, before we wrap everything up, let's look at our situation over here with the ice and the water. The ice has now melted completely, gone, and yet the water is still right at the tip. And the paper towel is still completely dry. So what's happened here is as the ice melted, the ice floats, so its density, as we saw in the iceberg example, is less than that of water. As the ice melted, it turned to denser water. And if you think about the iceberg example, you can work through this mathematically if you'd like, you will find that the change in the volume of the entire water as the ice melted was exactly zero. And that's why the water is still right up to the brim, and yet it hasn't overflowed. That, by the way, has important implications for what happens to sea level when ice melts. Ice that is floating in water, when it melts, as in this example, does not change the overall volume of the water at all. So the rise in sea level that we're worried about happening with global warming, for example, that rise is not going to come from melting sea ice. By the way, lots of other problems accrue from melting sea ice. Because it's fresh water, there are changes in the density associated with the surrounding salt ocean, and that can change ocean currents, and it can change the reflection of sunlight. Lots of other things happen. But melting sea ice will not cause sea level to rise. Melting land ice is an entirely different story because that's not floating, it's not displacing any water, and that will cause sea level rise. So there is our example that has some serious implications for a big environmental problem, sea level rise, but it tells us that melting sea ice is not going to contribute to sea level rise. Well, let's sum up, and then I'd like to give you a challenge. We can say that static fluids are characterized by density and pressure. Pressure increases with depth in hydrostatic equilibrium, and as we think about that hydrostatic equilibrium, we come to Archimedes' principle that the buoyancy force on a submerged object is equal to the weight of the displaced water. And let me end, in case you're interested, with a quick, simple mathematical challenge. I'm going to imagine you have a rectangular, flat-bottomed rowboat. It's got a mass of 120 kilograms, about 250 pounds when it's empty. It's 3 meters long, 1 meter wide, and 0.24 meters deep. I'm making it nice and simple for you because it's a nice rectangular shape. And here's the question. How many 85-kilogram people could it hold before swamping? Now, I'm not going to work through the details on this one, but I will point out that all that matters when we compare the density of an object with the density of the fluid for questions of whether it will float or sink is what is the average density? Because the only question is the mass of the displaced fluid more or less than the mass of the object in question? And so here's your problem. How many 85-kilogram people could it hold before swamping? Get out your pencil and paper or your calculator, work it out. Here's the answer. It could hold 6 people, a total of 590 kilograms of people, not counting the boat.